So we discuss we started to discuss Abel's theorem. We formulated Abel's theorem, but before we prove it, let us give some reformulations. Okay, but first, just a reminder what we defined. So we considered curves. So I just recall. So we consider curves. So we piecewise smooth maps from 0, 1 to x. Then we consider chains. Chain is a formal linear combination of curves. Then we have the group of chains. At the moment, X is an arbitrary Riemann surface. So, the group of chains. Then we have the map from chains to the divisors. Yes. Also, let us introduce the notion of closed curve. I don't remember whether we mentioned that. So closed curve. So means that so we have the map, boundary map from chains to divisors. Then the closed curve is a curve such that dc is equal to 0. Yes, closed curve. Then let us then Abel's theorem says the following. Now X is a compact Riemann surface. D is a divisor of degree 0. Then D is principal. If and only if there exists a chain such that the integral over C of omega is equal to 0 for any omega, for any holomorphic one form, and the boundary of C is equal to D. Yes, so this is the statement. Just some picture. Suppose you have some divisor. So suppose you have some points. Just to some illustration of what is happening. So suppose we have 4 points. Then we can draw curves. This is C1, C2, and then obviously, just an illustration to the definition, yeah, of DC. Yeah, then dC1 plus C2 is P2 plus P4 minus P1 minus P3. Okay. Yes. So we had it in the last lecture. Yeah, then there was immediately some questions. Also, I think Sergey mentioned Jacobian. Yeah, and then indeed, I think it is better to discuss some reformulations of Abel's theorem and then prove it. So, yeah, reformulation. In discussion. Yeah, first of all, consider, so we considered closed curves, but we can also consider closed chains. Yeah, so let us define Z1 of X as the group of chains that are closed. Yes. Yeah, and then simple remark that any closed chain is a linear combination of closed curves. Any closed chain is a linear combination of closed curves. Yes. Yeah, I mean, yeah, for example, how to draw something, I don't know, for example, we have some closed chain.
All these curves can overlap to each other?
Yeah, of course, yes. So we can, of course, we can have. Yes, so for example, like this, so you can, then it's a union of closed curves, so you can consider this curve, formally it's not so good to say like this. Okay, maybe because indeed, of course, formally it's not so good to say like this. Yeah, we just So yes, then so it's this is yes. Mm-hmm.
When you erase it, like, it's okay.
Yeah, I mean, yeah, I mean, yeah, I will say it again, but I mean, formally it's not so good to say like this because, yeah, I mean, I wanted to say that suppose you have some chain like this, yeah, then I wanted to say, okay, then this is a curve.
It's a loop, no?
Yeah, it's a loop, yeah, but I mean, yeah, but then I have to say how I construct a loop because a loop is a map from 0, 1 to, yeah, so. Yeah, then I have to say that, okay, I constructed from these pieces. Yeah.
But only, I don't know, I imagine like here only matters the base point because
Yes.
after when you take the boundary, like it goes to 0. No?
Mm-hmm.
I don't know, makes sense for me, but I didn't know you had to explain like how to construct it. Like, I don't know.
Yeah, I mean, yeah, I mean, I just want to because I mean, formally, yeah, of course, this is correct, but suppose you have some. Why I don't want to make a formal statement because suppose you have a chain C1 plus C2 plus C3, then okay, formally I cannot say that it's equal to this loop. Yes. Yeah. Yeah, but I will use it on the level of integrals. Yeah, I will say that this integral is equal to the integral over this loop. So, okay, then a period. Yeah, and then yeah, and then actually there is some correction to homework, just on level of definition because. In the homework, I said that a period of a form is an integral of a form over a closed curve, but actually the standard definition is that a period is an integral of a curve over any closed chain. So it's slightly, I mean, of course it's the same more or less, but this is a standard definition. So definition, so a period, so suppose you have some smooth form, then a period, of omega is an integral for some C for some closed chain. Yeah, so a period of omega is an integral for some closed chain. Yes. Okay. Yeah, and then indeed I want to maybe now make this remark. So suppose you have some point, your Riemann surface. Yeah, then I want to say that then there is a group homomorphism that I denote by integral from P1, the first fundamental group, to to I just want to say that okay. Or maybe first I must say the same for closed periods. So then a period is this, and we have a map integral from z1x to star. Yeah, indeed. If you have a closed chain, then you can integrate your forms over closed chains, and this gives a linear function on your forms. Yeah? So you have a map from closed chains to this space. Then I want to say that you also have a map from the fundamental group to this space.
That's the dual space of Lamarck form?
No. At the moment I want to consider just smooth forms. These guys are just...
Why the star? That's the dual space?
Yeah, dual, yeah, space of linear functions. And here I just want to say that, formally the fundamental group is the group of loops, continuous loops. And then we say that two loops are the same if they are homotopical to each other. Everything, and you can indeed any loop gamma in the any loop is homotopical to a smooth loop. Is a homotopical to a smooth loop. And also if two loops, two smooth loops are homotopical, then they are homotopical using a smooth homotopy. Then they are homotopical using smooth homotopy. Smooth homotopy. So if you have a loop, formally, your fundamental group consists of continuous loops, but there is some standard theorems from analysis that you can deform your loop a little bit and make it smooth. Yeah? So if you have a smooth arbitrary loop, you can deform it, make it smooth, and then the integral is well defined. But then, in order to check that this is a well-defined group homomorphism, you have to check that if two smooth loops are homotopical, then the integrals are the same. Yeah, but again, here you use some standard theory from analysis saying that if two smooth loops are homotopical, then they are homotopical using smooth homotopy. But then the integrals are the same by Stokes theorem. Yeah, so it's fine. Yeah, so we have this we have this, and yeah, and then yeah, I just want to say that if we want to consider, so I want to consider the image of this guy here, and then I just want to say that this image is the same as the image from the fundamental group. So lemma. So first I want to say that the images yeah, okay. So we have the map integral from z1 x. Now I want to consider harmonic forms. Yeah, so you have a smooth forms. Yeah, you can restrict. If you have a linear function on smooth forms, you can restrict it to harmonic. Yeah. So we have a map from the fundamental group to this guy. Then I want to say that the images are the same. The images are equal. Yeah, and then I want the same statement for when here you further restrict to holomorphic forms. So consider a map from z1x to holomorphic forms star, and also from p1 then the images are the same. Are the same. Yeah, I mean, and this is very simple. This is what I wanted to say in that remark that I erased. Yes, that yeah, you just suppose you have proof is yeah, it's very simple. You just say that suppose you have some some closed chain, then there exists closed curves C1 maybe tilde Cn tilde such that such that integral over C omega is equal to the sum alpha I integral over C. Then there's these closed curves, yeah, and constants alpha 1, alpha n, such that you can replace C by this linear combination of closed curves. Integral over Ci tilde omega for any omega for any smooth form. Yeah. Yeah, and then this is if you think about it, this is this is what I wanted to say. This is easy. Yeah. So if you have a closed chain, then it looks like it looks like a combination of loops constructed from curves. Yeah. So you can decompose it in this way, and then you can for each. So you can consider you can see that it's can be decomposed in these loops, and then you just choose loops here and here. Yeah. Yeah, I wanted to say that you can, if you have a closed chain C, then you can express it as a linear combination of circles, cycles. By a cycle, so maybe it's better to say indeed that a cycle. What is a cycle? Let us say that a cycle, or okay, not cycle, no, maybe circle. Okay. Or maybe circle chain. Let us say it's circle chain. Let us say that a circle chain is a chain that has this form. Yeah, that is a linear combination of curves of this form. Yeah? Then I want to say that any, it's easy to see that any closed chain is a linear combination of circle chains. And then, of course, if you consider a circle chain, then an integral over it is the same as an integral over closed loop like this. Yeah. Yes. So if you want to consider integrals over closed chain, then it's the same. You can equivalently consider integrals over linear combinations of closed curves. Yeah? So you can replace your chain by a linear combination of closed curves. But then I wanted to say that if I want to prove that the images from the, these two images here, these two images are the same, then I have to now move to closed curves that go from one point. Yes, but it's again easy. So if you have two loops that go from different points, then you can just you have this loop, you can just choose some path here, yeah, and construct this loop, and like this, and the same here. Yeah. Yes. So. Okay. So, is it clear? It's pretty obvious. Yeah. Then what I want to say. Now suppose that X is a compact Riemann surface. You consider the fundamental group from the topology course that it is generated by 2G generators. They are 2G generators. Then I want to prove a lemma. Say first, it considers this guy. I want to say that these guys. So you consider the integral over gamma I of something. This is a linear function on the space of harmonic one forms. Yeah. Then I want to say that these guys are linearly independent over C. Independent over C. And consider now the integral over gamma I as a linear function on the space of now holomorphic one points. Then they are linearly dependent over R. Independent over R. So you can consider integrals over these loops as linear as linear functions on harmonic forms, and then these linear functions are linearly dependent over C. But you also can consider them as linear functions on holomorphic forms, and then they are linearly dependent over R. Yeah, and the proof is simple.
Each one is like they are linearly independent from each other.
I mean, yeah, this is what I say.
Okay, the first one is linear independent between them, like in harmonic functions. Where you take all of them, they are.
Yeah, I don't understand. So here you take 2G linear functions. Yes, so I between 1 and 2G. So you have 2G linear functions. So this is space of dimension 2G, complex vector space of dimension 2G. So you have 2G elements. Then I just want to say that they are linearly dependent over C. Then you can consider them as functions on holomorphic forms. This is a vector space of complex dimension G. So as they cannot be linearly dependent, because I mean 2G is greater than G. But if this is a G-dimensional complex vector space, but 2G-dimensional real vector space, then I claim that these guys are linearly dependent over R. Yeah, then the proof is simple. Suppose not. Suppose not. Suppose they are not linearly dependent. Yeah. Then this matrix M then the matrix M is degenerate. Yeah, where you can consider the matrix of integrals over gamma I of omega j. And omega 1, omega 2g in harmonic is a basis. Yes, so so basically I is the first index. So basically, if these linear functions are not linearly dependent, then it means that the rows of this matrix are linearly dependent. Yes, but then also the columns linearly dependent. Yeah, then it's degenerate, and then you use that if the columns, if the rows are dependent, linearly dependent, then the columns are also linearly dependent. Yeah? Then there exist some constants without zero, such that, again, if the rows are linearly dependent, then the columns are linearly dependent. It means that there exists a linear combinations of omegas such that the integral over any loop is zero, such that the integral over gamma I of sum is zero for any I. For any I between 1 and 2g. But then you see, it means that any period of this form is zero. But then this means that this form is exact. But then, by the homework, there was some problem saying that if all the periods are zero, then the form is exact. Sum alpha g omega g is an exact form. But this is contradiction, yeah? Yeah, because because this form is a harmonic form. But we proved that actually the space of harmonic forms is orthogonal to this guy. Yeah? So they have a zero intersection. So it's a contradiction. So this means that these guys are linearly dependent over C. Yeah, and then the second part is an immediate consequence of the first part. What we say. Again, by contradiction, suppose not. Then there exist some constants some constants alpha 1, alpha 2g, some real constants, non-zero, such that the sum of the integrals over gamma I omega j is equal to 0 for any j between g and g, where omega 1 is a basis in the space of holomorphic forms. Is a basis. So you okay, suppose not, yeah, then these guys are linearly dependent over R. So some non-trivial linear combination is 0. So what it means? It means that there is some linear combination of gammas such that this integral, this sum of integrals for any holomorphic form is 0, or for any element of the basis in the space of holomorphic forms. But then I mean, alpha i's are real numbers. Yeah. Then you take the bar. But then some alpha I integrals gamma i's omega j bar is 0. For any j. But then you see, but then since omega 1, omega j, omega 1 bar is a basis. Yeah, well, we discussed that harmonic forms, the space of harmonic forms is a direct sum of holomorphic forms and anti-holomorphic forms. Yeah? So since these guys form a basis, we get contradiction with by part 1, by part we get a contradiction. Yeah, because we have obtained, so you see, omega j's, they form a omega j's and omega j bars, they form a basis in this space. So you have obtained that the linear combination of these integrals is 0 for any element of the basis here. But I mean, in part 1 we proved that this cannot happen. Yeah. Okay, so is it clear?
So automatically we get for the anti-holomorphic dual space too.
Yes, yeah, but yeah, of course. So is it clear? Yeah, okay, then we come to the definition of the Jacobian. So what we say? We say that so then definition. If X is a compact Riemann surface, then the group of periods is defined as the image of this map, integral map, from z1x to so it's a subgroup in the space of in the space that is dual to the space of homomorphic forms. So this is so this okay. This is called the group of periods. And then by this lemma, the group of periods is a lattice. So by the lemma, this is a lattice. Yeah, then one of the most important definitions. The quotient omega x star by the periods is called the Jacobian of x. So we have periods in this in the space lambda x dual. Then the quotient is called the Jacobian of x. Yes. So since it's the group of periods is a lattice, then the quotient topologically the quotient is homeomorphic to a torus. Yeah? So topologically. Jacobian of x is homeomorphic to S1 to the power 2g. Yes. Yeah, but by the definition, what is a lattice? Is a lattice. So, if you have some vector space over C, yeah, I mean it's by definition. So vector space over C, and then suppose you have some vectors. Yeah, I mean, dimension of V is equal to n, and suppose you have some vectors linearly independent over R. Yeah, then what they generate with integer coefficients is called a lattice. Yeah, then gamma. Indeed. Yeah, that's correct. Yes, I mean yeah. So then gamma, which is this, the sum of z gamma is called a lattice. Then gamma a lattice in V. So you have some vector space over C of dimension n, and you have 2n vectors linearly independent over R. Then gamma is equal to z gamma 1 plus etc. z gamma 2g is called a lattice in V. And here, this is exactly what we have here.
Since for the previous lemma, the one where we used the coefficients, or the one of
Yes. Of course, what we, I mean, here we of course combined two previous lemmas. Yeah, first we used that the image, this image, is the same as image from P1. Yeah, so we had a lemma saying that the images are the same. Then here we have generators gamma 1, gamma 2g, and then this means that the image is generated by the images of these guys. And then the last lemma says that the images of these guys are linearly independent over R.
So we take the first integers and then we extend it to the constants?
No, why? We don't extend. I mean, why?
In the proof we used coefficients in the integer for the proof of that.
Here?
No.
Yeah, indeed. Yeah, I mean, of course. I mean, when we considered z1x, we said that any closed chain can be obtained as a linear combination with integers of loops from P1, but with integers. So the image is generated by the integrals over these gammas with integer coefficients. Yes, and then the last lemma says that these integrals are linearly independent over R. So by definition, what they generate with integer coefficients is a lattice. Is a lattice. So we have these definitions, and we have the Jacobian. Then how to reformulate now Abel's theorem. Okay. What we have? Now we consider compact Riemann surface. Then consider the group of divisors of degree 0. So div 0x. Let this be the group of divisors of degree 0. And then also let us consider the group of principal divisors. Yeah? So div 0 per x this is the group of degree 0 divisors such that the group of principal divisors. D is principal. Yeah, of course. Yeah. So Yeah, but by the way, here we immediately, yeah, so we define these two guys, and the quotient is called the Picard group. Yeah, then pic 0 is div 0x quotient by div 0 per x. Picard group. Yes. Then what we have? Then we have a map. We can construct a map from div 0 to the Jacobian. So let us construct a map phi from div 0 to the Jacobian. How we do it? So indeed, take D, some divisor D, and choose some closed chain such that DC is equal to D. Yeah, we can always do it. Yes, so if we have some if you if divisor has degree 0, then it can be expressed as some point pi minus, oh, maybe it's obvious, yeah? So is it clear that any divisor of degree 0 can be expressed as a boundary of some, but no, why is Z1? C1. Is it clear? Okay. If, it's very simple. So any divisor of degree 0 can be written as a sum, one point minus other point. Yeah? So from I is equal to 1 to n. Yeah, then for example, you can take C equals sum of Ci's where DC where Ci connects Qi and Pi.
So C is actually Z1.
So this is Qi, this is Pi, Ci. Yeah, so any divisor of degree Z, of degree 0, can be expressed as a sum of, as in this way. And then since your Riemann surface is connected, you can connect Qi and Pi, and then take as C this sum of Ci's.
But then it was like the sum, a loop, like C was a loop since the beginning.
No, why? C is not a loop. I mean, the boundary of C is the divisor. And then we define phi of D as the following. So we take the integral over C and then take the projection. So the integral over C is what? Is the element of this belongs to omega x star. If you have a closed, if you have any chain, then you can consider the integral over it, and this gives an element of omega x dual. But then you take the projection, so where pi is the projection from omega x dual to the Jacobian. Yes. Is this clear? So you see here. So again, the definition. So if you want to define a map from degree 0 divisors to the Jacobian. The Jacobian is the quotient of omega x star by periods. So you have a divisor. You choose a chain such that dc equals d. Then the integral over this chain defines an element of omega x dual, and then you take the projection to the Jacobian. Then you have to check that this map doesn't depend on C. But this is clear. If you have some other divisor, some other chain, okay, maybe I write it. If C tilde satisfies dc tilde equals d, then, so because I mean here we made some choice of C. Suppose we chose another C tilde such that dc tilde equals d. There, but then dc minus C tilde belongs to the group of closed chains. And integral of C dot minus integral of C tilde dot. Yeah, this is this is integral of C minus C tilde dot. Then this belongs to periods, yes, because I mean integral over the closed chain is by definition a period. And so pi of this so thus the definition of phi doesn't depend on the choice of C. Yes. Yeah. Is it?
In the lemma we proved the linear independency. Did we get like an isomorphism between something between these maps of the integral
No, it's a surjective. It's a separate theorem. Yeah, it's of course it's surjective, but I will make a remark. Yeah, we will prove it, but it's not obvious.
I mean, this projection is defined on other.
No, what do you know? This projection?
Yeah,
I mean,
no,
this is of course surjective because I mean, Jacobian is just the quotient.
I want to say like there are things where the projection is acting that are not integrals over cubes. Like there are linear operators, but they are not.
Oh, can you say it again?
I want to see. In this space, there are linear transformations of the. Well, yeah, there are things that are not represented by integrals over cubes. Because this thing is not isomorphic to all the integrals over cubes, I guess. That's my question.
No, actually, this will be surjective.
Has this form?
Yes, it's a separate theorem. Yes, indeed, that any linear function on omega x can be written in this form as an integral over some chain.
So there was an isomorphism when we like between.
But we didn't prove it. You see, it will.
Okay.
But it will be. Yeah, but we will prove it. We will prove it. Yeah. So. So now, what is the reformulation? So we constructed a map from degree 0 divisors to the Jacobian. Yeah, what is important remark? Yeah, the first one is that Abel's theorem is equivalent to saying that the kernel of phi is the principal divisors. So do you is it clear? Yeah, because yeah.
That's the divisor to all the principles, like all of them.
Yeah. Yeah. So. So it is clear. Yeah? This is a reformulation of Abel's theory. That the yes.
So that means all are. The Jacobian was this by the theorem.
Yes. Okay. Yeah, I understand. Yeah, I mean, it's probably not immediate. Indeed. Let us prove this. Yes. Let us prove this. Suppose D is in the kernel formulate so yeah, I mean, it's really easy. So how you can reformulate this statement? This statement says that D is principal if integral over C such that dc equals D, this guy is a period of x, yes? Because I mean, this is the same, yes? But then you see, if this guy, if this integral belongs to the periods, so then this integral is equal to the integral so this statement is equivalent to this statement. But then you see, I mean, but the statement that the integral over C belongs to the period, this means that the integral over C is the same as the integral over some closed chain. Because it is a period if the fact that it is a period means that it's the integral over some closed chain. But then you can add this closed chain to C. Yes, D of C will be also dc will still be D. But then this statement is equivalent to the fact that you can find a chain such that dc is equal to D, and this integral is identically 0. Yeah. So. Is it clear? Yes. Yes. Yeah, and then the second remark is that we will prove that phi is actually surjective. Is surjective. So that this map phi from div 0 to yeah, and then and so we have the group of isomorphism peak 0x is isomorphic to the Jacobian. Yeah, so phi is the map from div 0 to Jacobian. So we will prove that phi is surjective. So this means that div0 quotient by the kernel is the Jacobian. But then, as I said, the kernel of phi is the principal divisor. So we obtain that peak 0, so the quotient of degree 0 divisors by principal divisors, is isomorphic to the Jacobian. So this is some standard fact. Then we have to finish. Then I wanted also to say that some remark about holomorphic line bundles. But yeah, maybe I will say it. Okay, maybe I don't have time. Because this peak 0 has also another interpretation. So peak 0, there is an isomorphism between peak 0 and the group of isomorphism classes of holomorphic line bundles over X of degree 0. So one can consider holomorphic line bundles over X. Then each line bundle has also a degree. And then actually the set of isomorphism classes of holomorphic line bundles of degree 0 over X is isomorphic to peak 0. So basically, then we have another statement saying that the set of isomorphism classes of line bundles over X of degree 0 is isomorphic to the Jacobian. The Jacobian has various interpretations. But yeah.
That also can be extended to other peak, maybe non-zero.
But they are all isomorphic to each other. Indeed, one can so one can consider divisors of degree d up to equivalence. Yeah, we had this equivalence of divisors saying that two divisors are equivalent if and only if the difference is a principal divisor. So you can take the quotient of d of d by equivalence, and then get peak d. But this peak d is isomorphic to peak 0.
Just curious, these chains, like there are chains from higher degree, like chains like in homology.
Yeah, of course. Yeah, of course. Here we speak about homology. Yeah.
So it was like points, curves, and what is the other is like simplex.
Yeah, of course. Yeah, I mean, here we consider Riemann surfaces, so complex manifolds of dimension 1. Yeah, so that is why we need only C1. But of course, there is a theory of complex manifolds of high dimension, and there they have all possible degrees. So they have to consider C2, C3, and so on. Okay. So today we had various interpretations of Jacobian and reformulations of Abel's theorem. Yeah, then I think the next lecture, and probably in the next 2 lectures, we will prove Abel's theorem. It's not so easy. Yeah. Regarding the test, контрольная работа. I think in order to save time, we will have a homework test. I will just give you problems for homework. Домашняя контрольная. Ну все, да, на сегодня все.